Next operation available in vector math is the dot product of two vectors. The dot product is defined as the cosine of the angle between two vectors, u and v, which is multiplied by the lengths of both vectors. This is a geometric definition of dot product, but there is also algebraic definition, which is used more often. And here you can see it's just simply a result of multiplying each vector's components x, y, and z together and adding them to generate the resulting dot product. So the resulting value is just a number, which is the scalar value, and an order of two vectors is not important. uv or vu yields the same result. A quick observation here is that if the length of two vectors are equal 1, which means they're normalized, then the result of dot product depends only on the angle between these two vectors. So of course, because cosine of 90 degrees is 0 and cosine of 0 degrees is 1, then the smaller this angle is, the larger will be the result. Right? So at the small angles, the dot product yields larger value. But if the angle keeps growing and we're getting close to 90-degree angles, at this stage, the dot product will be pretty close to 0. And in fact, if this is exactly 90-degree angle, cosine becomes 0 and we get 0 as a result. So let's summarize some of the properties of dot product, especially those that are important in 3D graphics. If the two vectors are of unit length, which means the length is 1, then the dot product is simply cosine of the angle between the vectors. So if we have two vectors which are not of unit length, they're just arbitrary length, we can actually take each individual vector and make them unit length. Right? So that now the two vectors are normalized and their length becomes 1. Right? So both vectors become of length 1. And that is typically done before we compute the dot product. Of course, there is a function in GLM where you can normalize your vector, basically bring the size of your vector, the length or the magnitude of the vector, to a unit length, and the function is named normalized. So let's just display the normalized vector. And when we run it, you see that the components of the vector are updated. And the idea behind it is that if we display the length of the normalized vector, we're expecting it to be of unit length. So let's verify this. And you can see that the result of this change is that the length of our vector QP now is 1 unit. So let's actually compute a dot product using GLM. And for this, let's add another vector. I call it x unit. So if we have our system of coordinates x, y, and z, then this unit vector, of course, is looking in the direction of x-axis because y and z are 0. So this unit vector is right here, and our vector QP is already normalized, unit length, and it's looking in some other direction. So let's compute the dot product, which of course will be equal the cosine of the angle between these two vectors, x unit and vector QP. In fact, let's change this to 0f. Right, so we specify floating point values and compute the dot product using dot in GLM namespace, and we provide these two vectors as parameters to this function call. The result is the scalar value dot product. So let's print the result, and of course this is really cosine of the angle between the two. Okay, and so this is the result. So it's negative 0.27. So let's inverse our vector QP one more time. Compute the dot product again and make it visible again. In fact, we can probably just inverse and do it like this. Now we can build again and run it. So this time the dot product became a positive value. Alright, so from this point on it should even be possible to find what is the actual angle between these two vectors. So here I'm trying to use the dot product, which is of course the cosine of the angle, and then taking arc cosine and converting it to degrees. Remember, all C++ math library functions return back the value in radians, or take the value as input parameter also in radians. So here we should be able to find out what is the angle between our two vectors. Okay, so the result is we get 74.5 degrees. Another property of dot product is that the magnitude or length of a vector can be successfully measured as the dot product of the vector with itself, and then computing the square root of this value. And because our vector QP is already normalized, we can try this formula. And so here normalized vector QP length is, so we compute basically the dot product of vector dot vector itself and the square root. So let's try this. Of course we should see 1 unit length, and so that's a way to compute the magnitude. So finally, if the two vectors are orthogonal, positioned at 90-degree angle, just like y and x, axis vectors, then u and v dot product equals 0, which is of course the cosine of 90 degree is 0. We can demonstrate this by the following example. So here what we're doing is that we're actually taking the x unit vector and the y unit vector and computing the dot product. So let's see the result. And the result is 0 as expected. So this way we can verify the 90-degree angle between the two vectors.